going to continue our discussion on Chapter 12 by branching into our major topic, which is waves. Okay? And so we're going to start off by just defining what a wave is, okay? And the fact of what it does and what its major purpose is. And perhaps the most important piece of the entire chapter, we're going to get in like the first 60 seconds. But when waves pass by an object, that object is moved. And so we should know from all our experience before that if an object is being moved, it takes a force to do that. And that force is going to be displacing that object. So when that object is being moved, there is work being done on it. Okay, and the example I like to give is if you have a rubber ducky in your bathtub. Okay, if you've ever seen a little kid in the bathtub or playing around with toys or even a pool or something like that, and again, the little rubber ducky comes floating by and they get excited, they start splashing up and down. And what happens, those waves then cause that rubber ducky to bounce up and down. Well, what's happening is the child is putting energy into the water by splashing and filling their hands. Those waves then carry that energy out, and that causes work to be done on the duck. And so perhaps the most important thing in the entire chapter is that we say that waves carry energy. And energy's kind of been a big thing. And actually, I'm going to write it out again because it's so important. It's worth writing out. Waves carry energy. And so we've been talking about energy in mechanics. We talked about how in electricity, those charges moving through our circuit carry energy. Now we're looking at another way that energy is transported from spot to spot to spot in the terms of waves. So we're going to talk about our major topic in these next two chapters, chapters 12 and 13. We're going to focus on mechanical waves. And mechanical waves are waves that require a medium to travel through. And probably the best example is if you want to have a water wave, you need water. Without water, there can't be a water wave. With sound, you need something that can vibrate. If you want to have waves going down a spring or a string or something like that, you need that material. And so we're going to deal with just those waves that require a medium to travel through. Later on, chapters 14, 15, and 16, we will talk about electromagnetic waves. That's the other type of waves we'll investigate, waves that do not require a medium to travel through. Okay? So the waves we're going to talk about are mechanical waves, require a medium. Now, going to have to define a couple different things about these waves again, just like we defined stuff before with simple harmonic motion. If we have a single wave traveling through a medium, we're going to give that the name a pulse. It's just one little blip of energy that's traveling out through the medium, one thing just going out. There's a blip. The example I like to give too is if you've ever seen The Hunt for Red October, old movie, but if the sonar, they ask for one ping, and that sends out a sound wave to try and identify what's out there. Okay, that single ping is a single pulse, one little blip of energy traveling out. This is opposed to a periodic wave, which is a wave that will regularly repeat itself. It's very similar to simple harmonic motion. So a single blip of energy, one little splash in the pool, that's a pulse. If you're splashing up and down, up and down, up and down at a regular rate, that's what's called a periodic wave. We're going to deal with both types as we look at this. Now, sine waves, you should remember, you should have had some conversation about sine waves in mathematics. Sine, cosine, that kind of thing. You probably remember them looking like this, okay? And it turns out that they appear in nature as well. In fact, any source, this object is any wave source that's vibrating with simple harmonic motion will produce this sine wave. And so if I were to take these and vibrate them up down, if I had a little pool of water where to go splash, 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 it would generate this sine wave traveling out from that splash, splash, splash. So sine waves have their source being simple harmonic motion. Now, we're actually going to break up mechanical waves into two types. The first are called transverse. And I'm actually going to diagram these out, and I'll probably move that diagram down. But a transverse wave actually looks exactly like that sine wave that I just drew before. So our wave motion is, in my case, the way I'm drawing it, is going to be traveling from left to right. And so the wave's doing this as it travels out. Well, in the process, as that wave travels out, the individual particles, now you have to remember, there is a medium that this thing is traveling through. This right here is our undisturbed medium. Undisturbed. So you can think of the water that's originally crystal flat, nice and flat, okay, and then something comes along and disturbs it, splashes in it, you're going to get this wave. So the wave travels out. That's going to cause that medium, particles which then, to vibrate up and down as the wave travels through. So if you watch my hand goes down, then up, then down, then up. My wave is traveling from here over to there, but my hand is traveling up and down. And so this is kind of the definition of a transverse wave. It's going to cause particles which they pass to vibrate at right angles. And so my velocity of the wave is horizontal. My particle motion is perpendicular to that. And so the way that I like to remember it is with a transverse wave, a transverse starts with the letter T. Well, T, if I invert it, is just a perpendicular sign. And so I remember, oh, it makes the T. That means the particles are perpendicular, moving perpendicular to the rest of the wave. Okay, so that's what a transverse wave is. Now, we're going to label parts of this. So I'm going to come down here and I'm going to redraw this just so you can get it. Okay, but if I redraw this, here's my transverse wave again. Again, I'll put in, here's my velocity, my wave motion, or particle motion is perpendicular. I'm going to put in my undisturbed medium again. And I'll put that as UDM, undisturbed medium. Okay? But the crest, that's going to be the highest part of the wave. So I'll label that with a red X. This is my crest. And here's my crest. Whereas opposed to the trough, I'll put that in purple. That's my lowest part of the wave. Now, as we remember from discussing in simple harmonic motion yesterday, we talk about the amplitude. The amplitude is from the undisturbed medium to the crest. Now I'll label that with just an A for amplitude. Or from the undisturbed medium down to the trough. The largest amount of displacement is going to be what's called my amplitude. Okay? Now the other thing I have listed up here is the wavelength. Okay, so crest you can say is the highest part. So highest, the trough is the lowest part. Wow, that's not even legible. I apologize for that. Let me try that again. Let's put it in black. Crest, highest. The trough is the lowest. And the wavelength literally stands for the length of one wave. Now, just like before, when we talked about yesterday with simple harmonic motion, one vibration, one oscillation is an up and a down. The same thing happens here. A wavelength is both a crest and a trough. And so my wavelength, which I'll put in, let's see, what color do I want here? I will put that in blue. My wavelength is both a crest and a trough. So a whole crest and a whole trough, this is a wavelength. Now, I don't want to write out the word wavelength anymore because it's too long, it's too cumbersome. And it turns out the wavelength has its own symbol. The symbol of wavelength is the Greek letter lambda, which kind of looks like a one-legged pi symbol or I don't know, it's a lambda. I don't know how to describe it. I always describe it as one-legged pi. Okay, so instead of me writing wavelength every time now, I'm going to say, oh, that's one wavelength, one lambda. And its units, obviously, units are going to be meters. because it's the length, distance of one wave. Now, this is one wavelength that I've got diagrammed here, but it also, because it could be this, it could also go from crest to crest. This is one complete wave as well. So that's one wavelength. Or I could go trough to trough. That's one whole wavelength. But it's got to be one complete wave from start to finish. Just like before we talked about one complete oscillation for simple harmonic motion. All right, so that is our transverse wave. The second type of wave is called longitudinal. And so with transverse, as the wave traveled from left to right, the particles would vibrate perpendicular. A longitudinal wave, the particles travel parallel. And so this is a little bit tougher to diagram. And I'm going to give you a demonstration. I'll show you, I'll have put a video link in here so you can see it, or I'll demonstrate it tomorrow in class. But what's going to happen is you get a compression and an expansion, and a compression and an expansion, and then a compression and then an expansion. And so what ends up happening is your wave will still be traveling, in my case, from left to right. So there's my velocity of wave. But now my particles are going to vibrate parallel to the direction of motion. And so what ends up being is, so if you were looking at it like this, as my wave travels from this way, from left to right, the particles are actually going to vibrate like this as it goes along. The best example of this that I can give, and we're going to spend a whole chapter on it, next chapter coming up, is sound. Okay? For those of you who went through earth science, these two waves are also in earth science. The P waves, pressure waves, are longitudinal like this, and they shake things like this as the earthquake goes by. The S waves, the secondary ones, are shaped like this, and they shake things up and down as the wave goes by. Okay, so this is my particle motion. Okay, so the particles are vibrating parallel. And again, this will be a little bit better once I show you the animation, or once I demonstrate this in class. You'll be able to see it a lot more and go, oh. But basically, it's doing this as it travels along. The particles are vibrating parallel to the direction of motion. Now, I also have to label parts of these as well. And so I'm going to just go back up to my original one so you can see it. But parts where they are close together, this is what's called a compression, because they're closer together. Parts where they're further apart, I'll put this in purple, that's an expansion. Or an elongation, but they're further apart. Okay? You'll also hear me refer to it once we get to sound as being a rarefaction. Rarefaction is a region of lower air density. Okay? But compression, expansion, you get the idea. We also still have a wavelength in here. The wavelength is the length of one complete wave. So from compression to compression, or expansion to expansion. But it's got to be one complete wavelength in there. Now, the other thing that I put down on this slide was the density graph. And if you look, if I were to look at the density, compressions are regions of spots of high density. And so if I were to do a density graph of this, I have a spot of high density, spot of low density, spot of high density, spot of low density, high density, low density. And so your density graph actually looks very much like a transverse or a sine graph. And so just like with our ones before, with any wave source that vibrates with simple harmonic motion, we'll create a sine graph. Now, the longitudinal one doesn't look originally like a sine graph, but once you change it to the density, there's that sine graph that we talked about before. So here's our spot of compression, or high density. Pen is massively messed up today. Compression, so high density, and here's my expansion. I just got to write slower. Okay, so high density. And then low density. There's that sine graph that we talked about before. So these are the two different types of waves. So we've got a compression, our elongation, our wavelength, density graph we've got there. Now, some people also ask about, hey, well, what about the amplitude? And the amplitude will be how big, how wide it is. It's how many particles it carries. Very rarely will you get an amplitude question on the Regents exam on a longitudinal wave. Okay, we'll talk about basically amplitude refers to how much energy it's carried there. So we'll talk about that a little bit more when the time comes. Now, the other thing I've been referencing a lot is a water wave, and the fact that, oh, water waves are transverse. Well, they're not really. They're actually a combination of both longitudinal and transverse. Okay, and so what ends up happening is, and I'll kind of zoom in on this diagram, as the water wave goes by, what's going to happen is, yes, you do have this up and down motion, which I'll put in red. So you do have this up and down motion as the particles bob by, yeah. But you also, at the same time, have these particles moving forward and back. And if you've ever been out on a boat when those waves are going by, you kind of get that feeling where you're pushed forward and up and then down and back and forward and up and then down and back. And so you end up being in a circular motion. And so water waves are actually both transverse and longitudinal. Okay? And this is what happens as this thing gets bigger. At the top, you get these big circle of motion. As you get further down, the circles get less and less and less. Now, just a side note, when you get a tsunami, which is a huge wave, these circles of motion, these huge circles of motion are really big all the way down, further down. And so when it gets to the seafloor, now all of a sudden these waves get huge because they're pushed up. Those big circles are actually in there, are actually lower down as well. So when it gets to the surface and the seafloor starts pushing it up, that energy makes those waves really, really big. Now, the other type of wave, water wave that I want to talk about is what happens if you throw something into a pond. And most everybody's seen that before. Or if you drop something, you make a little splash in there, you get that little blip in the middle, but then you get ripples that go out, that expand further out. And the direction of motion, there's my velocity of my wave. And I'm not going to put them all in, but this velocity of motion is always perpendicular to the wavefront. These black lines are the wavefronts. And these green lines are showing the direction of the velocity. These actually have a name. They're called rays. And they show the direction the wave is moving. At that point. Now, the only reason I bring this up is because you can very easily visualize this. So if you throw something into a pond or something like that, you can actually visualize this going out. Like, oh yeah, I can kind of see how that would show the direction. We're going to end up using rays in terms of waves that we can't see. We use rays to describe light and how they move in a straight line. And those rays show the direction of motion of that light wave. So I'm going to reference this in a couple chapters from now, but I want to give you a visualization now of what we're talking about, how the rays show the direction that the wave is moving, and I need to put that are perpendicular to the wavefront. Now, there's one more thing I want to talk about in this before we call it a day, in the fact that sometimes we want to know how fast these waves are traveling. So remember, from very, very first equation I ever taught you was that the speed of an object could be found by taking the distance that object travels and dividing it by the amount of time that it takes to travel that. Well, in terms of waves, we have things that reference that. Instead of using the distance that it travels, we can say, oh, I know the length of one wave. That's the length, that's a distance one wave takes during that time. That's a wavelength. And then the time it takes for one wave, that's known as the period. And so I can find the speed of a wave, v wave, by taking the wavelength and dividing it by the period. But there's another way to write this, because remember, and I'll put this over here, remember, frequency is equal to 1 over the period. And so I can, instead of, let's say I don't know period, I know the frequency, I can rewrite this as velocity is equal to the frequency times the wavelength. And so this will give us the speed of a wave. And this equation is in your reference tables. So we'll practice with these tomorrow. We'll do a couple sample problems. We'll discuss those other waves a little bit more, and then we'll do some homework on it. And then we'll finish off the chapter tomorrow with all of the other phenomena of waves that we're going to describe in terms of these, but then also apply to all the other waves we're going to discuss this year. All right, so that's it. Everybody have a great day. We'll see you later. Bye.